Hi, ladies and gentlemen. We're moving on with our discussion of root finding. Now we're going to talk about the secant method, which is related to regula falsi and also Newton's method. And I'll show you the derivation of Newton's method. So, starting with the secant method, the issue with the secant method is, and the methods that we discuss going forward, we are going to give up on the bracketing requirement. We are, for these methods, not going to be guaranteed of success, which means stability becomes an important factor for us. With bracketing methods, the stability is guaranteed, and we are simply trading speed and accuracy. And so this situation is a little bit different. You'll notice here on page 68, the product of the function values is not necessarily less than 0. And I'm going to show you what this looks like. But first of all, an important discussion about the derivation of the secant method. Here is the equation of a line, similar to what we were doing in regula falsi. The difference is we are no longer tracking the endpoints of our interval. So what we're going to do instead is take on an indexing notation where we just track each subsequent approximation for the root. So we're going to start with, in this case, x naught and x1 as the endpoints, as any 2 points, and then we will generate an approximation for the next point, which is x2. And that approximation will be based upon the previous 2 approximations and the secant line. That's what we're doing, is we're using the previous 2 approximations to build the secant line. So what I want to point out to you is this is the formulation that looks like regula falsi. This formulation is more common because what we're doing is, instead of using x naught for the function evaluation and for the argument with x minus x naught, we're using the most recent approximation that we have, which is x1. So we use the function evaluation at x1 as well as x minus x1. And that gives us this general form for the secant method, which I've highlighted here in the algorithm. So this next set of steps is the algorithm that you're going to program in MATLAB. We'll do that in class. And here you can see the tolerance check is an absolute error tolerance check, not our preferred method. But as always, you want to program in some different methods so that you understand the differences between one method over another. So let's take a look at the most significant difference with secant method. Here's exactly the same problem we talked about with regula falsi. And you can see the 2 endpoints, and the way that my color coding is working is I have the gray point is the approximation from 2 steps prior. The purple point is the last approximation, and the magenta point is the next approximation. So what we'll end up doing is we'll end up using the magenta and the purple to make the next secant line. So you'll see the next secant line is going to connect the purple and the magenta, and then they'll all change colors. So the purple becomes gray, the magenta becomes the purple, and then we have a new magenta because that's our next approximation. What's going to happen now is the gray is 2 steps old, and that's going to get dropped, and we're going to build the secant line here between these 2 points. So this is a demonstration of how we've given up bracketing. We're now using 2 points that do not contain in the interval the root. So on the next step, we have the secant line through these 2 points, and what you'll notice is we have an approximation that actually exceeds our original interval. Our original interval was from 1 to 2, and here we're all the way out beyond 2, and that's the next point. So our next secant line is going to be between the magenta and the purple, and then all the colors will update. And now we're just going to continue to move in. We have those 2, and again we have 2 points here that do not in the interval contain the root, but we're going to use that secant line to shoot up and give us an approximation. And as we continue, we can see that we are coming in closer and closer to approximating the root until we finally end up with the points so close together we can't differentiate them. But this right here is the hallmark of the secant method, as opposed to regula falsi. We are using 2 points that do not bracket the root that we're concerned about. So that's really the idea. That's this conversation right here. You can see the line, which is drawn right here, which is the same one we have. And there's more discussion about this. So this brings up the point about stability. And I've given you an example problem that you should use in every situation to check your algorithm as well as your initial guesses. So that's this hyperbolic tangent. The hyperbolic tangent is an excellent function for application throughout numerical analysis because it's effective at breaking many algorithms. But what I want to do is just talk about a different example, similar to what we talked about last time, to demonstrate the stability. I've jumped back in the file here, and you'll notice that my initial guess was 1. So the interval was originally 1 and 2. Remember, the secant method requires 2 initial approximations. If I change this to 0.7, I'm going to rerun the code, and you'll see what happens. So now I'm out here at 0.7 instead of at 1. And so, okay, we can draw a secant line, and we can come up with our approximation, and now we're going to draw a secant line in here. That's no problem. The issue comes with the next step. The next secant line connects the purple and magenta dots. So the next secant line is this one. And now we're sunk. We can see we have a line with a slope that's almost 0. So we don't know where that line will intersect the x-axis. So we don't know where that approximation is going to be, but it's going to be way out at the end, and it's going to destroy our approximating capability. In fact, this algorithm comes up with something completely ridiculous. It comes up with a near vertical line because it cannot find the value that we were trying to do to approximate. So this is the stability issue. The secant method works really well when we have something that is approximately straight. Let me rerun an example with a different function. So in this case, what I'm going to do, actually I'm not going to rerun this one with a different function. I'll show you the function that we talked about previously. So in this situation, we have the secant, and this is the regula falsi, but it would work similarly, although the secant method's even faster, because in here we would have a secant between these two lines, which would bring us in really closely. So there are advantages and disadvantages to all of these methods. One of the big disadvantages for secant is stability. So let's take a look at what we have here. These are some more examples. You can look through those. Those are in the text. As well as a comparison with regula falsi, and then we have all of the exercises. So 2 notes on the exercises. Remember, once you have programmed your secant method, you're going to execute on all of the homework problems. The other one is that we've completely lost any association here with the numbers. So we have things like this. How does this compare with problem number 6? So is that problem number 26? I think so, but I can't guarantee that. Here's the bottom line. We have many similar problems that we're using for different root finding methods. And the goal is that you solve these problems using bisection, using regula falsi, using the secant method, using Newton's method, so that you can kind of compare and contrast the different approaches. So if you can't figure out which problem these are referencing, first of all, my apologies. That this is not straightened out. This is what you get when the book is free. But just look back and solve a similar type of problem. Look at how it worked out with a different method. All right, let's take a look at Newton's method. All right, with Newton's method, what we're going to do is, you notice with the secant, this is the secant method right here. So with the secant method, we have an approximation for the slope. We've taken the approximation for the slope over or using the previous 2 approximations to the root. So if instead of approximating the slope, we can actually calculate the slope, does that improve what we're doing? And the answer is a resounding yes. Newton's method is one of the most popular and most frequently used root finding techniques available. So it does have a limitation, of course. We have to be able to calculate the derivative of whatever our function is. So the derivation for Newton's method is provided here. It really comes from a Taylor polynomial, but I want to write this up in a little bit more complete manner and discuss it, because this is the heart of how Taylor polynomials apply to root finding. So the approximation that we were using for Newton's method is really, we are approximating the function f about our current root approximation. So what we have is, we have this function value, and I've just built out the Taylor polynomial here. So you can see we have our linear term and we have our quadratic term, and then we just have more and more and more terms. And what we are seeking is xn plus 1. So we're seeking the next x approximation that gives us a zero function value. Remember, that's what we're trying to accomplish. We're trying to make this thing zero. So if we now assume that we just are going to use the first order approximation, we have this, which we can easily solve. That's going to give us xn plus 1 is equal to, and I'll have xn on the other side, and I'll have minus an f of xn divided by an f prime of xn. And that's it. That's all Newton's method is just the recognition that, hey, we can truncate a Taylor series and just use a first order polynomial to try to approximate values for roots. It turns out that this is a really effective method. We could, in fact, if we knew the second derivative, we could improve upon this. And we do that sometimes, but not frequently, because Newton's method is so good. It doesn't really help us to use this next level. When we talk about the rate of convergence for these different methods, you will see that Newton's method is extremely fast, but it does suffer from some stability issues. All right, this conversation we just had is the one that's outlined here on pages 72 and 73 of the textbook. And we again see the relationship, the tie-in between Newton's method and the secant method. So oftentimes we use the secant method because we cannot find the derivative of a function. But it's important to understand the connection between the two things. There is one aspect to note. Newton's method is different from all of the methods we've discussed thus far because it requires only a single initial value. We do not have to have two values to start the process. And then here's a conversation which I'll pull up my Mathematica and I'll show you a similar type of conversation here. And we do have the algorithm that follows right here. And again, we've included the absolute error for the tolerance check, but that's not necessarily the best. Relative error and functional are also good. So here's the approximation that we have for, and all I've done is gone into the midpoint of the interval that we've been talking about previously, from A at 1 and B out here at 2. And what we're doing now is there is no secant. The line that we are finding the intersection of is the line that's created by the derivative. So the concept is exactly the same as secant and regula falsi. We're going to develop a line, but instead of it being a secant line, it's going to be a tangent line, tangent to the curve. So as we move forward then, we have this approximation for the root right here. We go to that function value, and again we use the tangent line. And then we're going to close in with our next approximation. And it turns out that the convergence here is quite rapid. After only 6 iterations, we are to the point where we will not see the approximation in X move anymore. So it's an excellent method and it's used broadly. There are a couple of examples pointed out in the textbook. This example here is the one that we're looking at. And it's important to try some different initial conditions. What if we had selected 1.2 as our initial condition instead of the midpoint of 1.5? Well, if we had selected 1.2, we'd have the same problem we have the secant. We would be right here and the tangent line would be nearly horizontal. We would have a slope value of almost 0. And what are we doing with that slope value? We're dividing by it. So we would be dividing by a number that's almost zero, and that is always trouble. So Newton's method does suffer from stability issues just like the secant. Some examples about how Newton's method is used today are provided here. One of them is in solving square root problems. Another one is just division in the computer. So the computer has no capacity to divide numbers. The numbers can be added and the numbers can be multiplied based upon the 64-bit representation. It's easy to add those numbers together, and it's easy to multiply those numbers by adding their exponents and then multiplying their mantisses. But we have no means of dividing. Dividing is done using Newton's method. And I'll let you read about this. It's an extremely important example. Just like the square root is also an important example. We don't think of it because we just type square root in. But the machine does not have a magic capacity to find square roots of numbers. And so there are techniques to do this, Newton's method being one of the more popular. And then, of course, same issue as we have previously. You're going to work all of the problems here in the exercises, which basically means once you've developed your Newton's method, then you'll apply it to these different problems. And we have the same issue as before with the references to the prior problems, but you'll notice the similarities. We have the negative x to the 13th problem again. We have the sine of natural log of x squared again. So it's a repetition of these different problems which you will solve using the variety of algorithms that we've discussed. That's it. I look forward to seeing you in class.